Welcome. In previous modules, we have neglected mass transport processes in the bulk water. This module here will introduce an approach to quantify the influence of external mass transfer resistance on biofilm processes. Here's a schematic that you might know from fluid dynamics. Many people know such flow velocity profiles describing a hydrodynamic boundary layer. If there's a hydrodynamic boundary layer outside the biofilm, it is reasonable to expect that this has an influence on substrate availability in the biofilm. At the end of this lecture, you should be able to explain why substrate concentrations at the biofilm surface are smaller than in the bulk liquid. You should be able to develop a model to describe substrate diffusion in the external mass transfer boundary layer. You should be able to link mass balances for external mass transfer and within the biofilm. And you should be able to determine the relevance of considering external mass transfer resistance to biofilm reactors. Here's a schematic of our biofilm where we now show a gradual transition of bulk phase substrate concentrations close to the biofilm surface. To simplify our analysis, we introduce the concept of an external mass transfer boundary layer with a linear increase in the mass transport boundary layer until it reaches bulk phase substrate concentrations. This conceptual model matches observations. In measurements, we can observe that substrate concentrations at the biofilm surface are smaller than bulk phase concentrations. The concept of an external mass transfer boundary layer can be used to quantify this effect. In the external mass transfer boundary layer, there is no biomass. The only process is mass transport by diffusion. Using Fick's first law, we can calculate the flux in this boundary layer from the concentration gradient and the diffusion coefficient. The concentration gradient is calculated from the difference between bulk phase and biofilm surface concentrations and the thickness of the external mass transfer boundary layer that we will call L sub L. We often combine the boundary layer thickness and the diffusion coefficient into a single mass transfer resistance parameter. With this, we can rearrange the equation as shown here. Based on the principle of mass conservation, the flux of substrate at the surface of the biofilm must equal the flux of substrate through the boundary layer. This is shown here. The flux at the biofilm surface of the biofilm here is assuming first-order kinetics inside the biofilm. We can solve this equation to calculate the substrate concentration at the surface of the biofilm. Substituting the value of SLF, so at the surface of the biofilm, in the biofilm flux equation, we can now calculate the substrate flux into the biofilm, considering now also the external mass transfer resistance. It is useful to evaluate some extreme cases. For very small external mass transfer resistance or very small first-order rate constants, we can neglect the effect of an external mass transfer resistance. This solution converges to the solution we had derived in previous modules. In case of very large external mass transfer resistance or very large first-order rate constants, the substrate flux is dominated by external mass transfer resistance. The flux is no longer a function of processes inside the biofilm, but only considers the external resistance. The corresponding concentration profiles are shown here. On the right, we see the situation where the effect of external mass transfer resistance can be neglected. On the left, we see the situation where processes inside the biofilm are so fast that substrate concentration at the surface are close to zero and the overall rate is determined by external mass transfer resistance. Here is an example considering monokinetics for substrate degradation inside the biofilm. Bulk phase organic substrate concentrations are shown on the x-axis. On the y-axis, there is the flux of organic substrate. The different curves in this plot correspond to different boundary layer thicknesses, L sub L. We can see that external mass transfer resistance can have a significant influence on substrate fluxes. This means two things. We must consider external mass transfer in our mathematical models when we use these models for design or optimizing operation. And number two, if we operate a biofilm reactor and we want to improve overall reactor performance, then we also need to consider how mixing conditions can influence the thickness of this external mass transfer boundary layer. Typical external mass transfer boundary layer thicknesses range from 30 to 100 micrometers. The boundary layer thickness is influenced by mixing conditions. Thus, increasing aeration can increase nitrification in two ways. Increasing aeration increases bulk phase oxygen concentrations, but increasing aeration can also decrease the thickness of the external mass transfer boundary layer. We can see that biofilms are complicated systems. Here are the take-home messages from the current module. External mass transfer resistances usually have a significant influence on overall substrate removal rates. They must be considered in the practical application of biofilm models for reactor design or operation. Typical values of the external boundary layer thickness range from 30 to 100 micrometers for most reactors, but external mass transfer resistances depend on mixing conditions and on biofilm morphology. We derived solutions making the following assumptions. Mass transfer in the external mass transfer boundary layer is by diffusion only. Substrate flux at the surface of the biofilm must equal the flux in the boundary layer.